I'll be going over the Dess-Martin-Periodinane reaction, also known as Dess-Martin oxidation. So it is a oxidizing agent which converts primary alcohols into aldehydes, secondary alcohols into ketones, and tertiary alcohols do not react, so no reaction. It's important to note that primary alcohols only convert to aldehydes in the absence of water, so without water. Some examples, so if you have a primary alcohol like this, and you know this is primary because this carbon is only bound to one other carbon right here, and this will be converted into an aldehyde, which looks like this. If you have a secondary alcohol, and you know this is secondary because this carbon right here is bound to two other carbons, will be converted to a ketone, which looks like this. So you may be wondering, why use this when there are so many other oxidizing agents? So some pros, and the most important one, is that it is a green reagent. Meaning that it doesn't produce toxic byproducts compared to other oxidizing agents. For example, a lot of other oxidizing agents use chromium, and this one does not. There is no cooling or heating required. Some reactions require cooling to negative 78 degrees Celsius, which can be a pain sometimes. And there also is a higher yield. A con to this is that it is more expensive. I'll now go over the reagents used in this reaction. This reaction is comprised of this molecule right here, which has 3 OAC groups or acetate groups bound to iodine. This iodine might look a little weird because typically iodine is bound to one other atom, such as HI or HBr. This iodine is called a hypervalent iodine. Iodine being bound to many different atoms gives it a high oxidation state, making it a good oxidizing agent. Also, as you can see here, each acetate group has an oxygen. Oxygen is highly electronegative, which will pull electron density towards itself. So it'll pull electron density away from this iodine, giving the iodine a partial positive charge, which is important, and I'll show this later on. Also, a base is necessary. You can use triethylamine, but it is not necessary because there are conjugate bases which are produced, such as OAC negative, and I'll explain this later on. I'll now go over the mechanism of this reaction. So here we have a secondary alcohol, which has 2 lone pairs, and these 2 lone pairs will give the oxygen a partial negative charge. This oxygen will then attack the iodine, which has a partial positive charge, and will kick off an OAC group. That will form this molecule over here, which will have a positive charge on the oxygen. The OAC leaving group, which has a negative charge now, will then attack this hydrogen, deprotonating it, and will donate its electrons to this oxygen to create this neutral molecule over here. Then, at the alpha position to the oxygen, there's a hydrogen, which will also be deprotonated in a E2 mechanism. And this can be done using any base that's formed in the reaction or by triethylamine. So you could use OAC negative, which was produced earlier, or any conjugate base, or you can also add triethylamine to this. So for this mechanism, I'll just use triethylamine. So this will deprotonate the hydrogen, which will donate its electrons here, and to prevent hypervalency, this bond will donate to the iodine, and another OAC group will leave. This will form this molecule over here, and it will also create this ketone, since we started with a secondary alcohol, which looks like this. You'll also create some byproducts. So since I use triethylamine, when it becomes protonated it creates this charged molecule right here. If I were to use OAC negative as my base, it would create acetic acid, since there is a added hydrogen. And acetic acid is basically vinegar, which shows that the byproducts are not toxic. And I'll go over some examples. So again, we're starting with a primary alcohol now, and this oxygen will have 2 lone pairs, giving it a partial negative charge. This partial negative charge will then attack the partial positive charge on the iodine, which will then kick off an OAC group. This then forms this molecule over here, which has a positive charge on the oxygen. And it will also form OAC negative, which will act as a base. This base will then deprotonate this hydrogen, donate its electrons to the oxygen, and will create this neutral molecule. This neutral molecule, at the alpha position to the oxygen, has 2 hydrogens. Since they both are symmetrical, or the same, one of them will be deprotonated and will form a double bond in a E2 mechanism. So here, again, you can use triethylamine or any conjugate base, so like OAC negative. For this example, I'll just use OAC negative. So OAC negative will act as a base. We'll grab this hydrogen and we'll donate it over here. And then again, to prevent hypervalency, this bond over here will be donated to the iodine, which will then kick off an OAC group. This then forms this aldehyde product, since we started with a primary alcohol, which looks like this. And then again, we also have byproducts. And in this case, since we used OAC negative as our base and did not add triethylamine, we end up with acetic acid as our base. We could have produced this product over here, but I didn't add triethylamine this time. But you could use that instead. I'll do one more example. So here, this time we're starting with a secondary alcohol, which again has 2 lone pairs. This oxygen group has a partial negative charge, which will then attack the partial positive charge of the iodine, and this will kick off an OAC group. This then forms this molecule over here, which has a positive charge on the oxygen. The OAC group that left, which has a negative charge now, then acts as a base and will deprotonate this hydrogen and will donate its electrons to the oxygen, creating this neutral molecule over here. Next, at the alpha position, the hydrogen that's there will be deprotonated, and this again can be done by triethylamine or by OAC negative. It doesn't matter which. Here I'll just use OAC negative. So this will grab this hydrogen, which will then donate its electrons here, and to prevent hypervalency, we'll donate them to iodine, and we'll kick off an OAC group. This then forms this molecule again, and will create a ketone since we started with a secondary alcohol. And then these are the byproducts, and since we used OAC negative, we'll end up with acetic acid. And that's it.